In this lecture, I'm gonna highlight for us four different categories or groupings of ion selective electrodes. And the heart of it, the heart of an ion selective electrode is a selective membrane, that is used to make that particular sensor or ion selective electrode. So there are four major types of ion selective electrodes, starting with the simplest and the commonest of them, which is a glass membrane. And I think I've already talked about it, before. So the glass membrane, is what you would call, the pH sensor, the pH ion selective electrode. Glass, has got good selectivity, particularly to hydronium ion. Of course, that's why it's a pH sensor, but it's not completely, or 100% selective, to hydronium ion. It also tends, to respond a little bit, to the sodium ions and also things like the silver ions and so on. And so you would find, the pH electrodes tend to interfere, with sodium ions. So particularly when you're trying to analyze salt water or seawater, that has got a lot of salt in it, then often you tend to get the pH electrode being fairly inaccurate, because of that interference. However, it's the most common and very commonly used in lots of application, right? In agriculture, in the lab, you guys use a pH electrode all the time. And so it's a good basis, for us to understand ion selective electrodes. Now, this glass membrane, one huge advantage of it, of course, it has excellent chemical durability, even in very, aggressive types of solvents, so it can be used. Now, take note of this. Ion selective electrode made of glass membrane or a pH sensor. Like we said before, it has, an indicator electrode, and that's what I have here. It has an indicator electrode, but also it has a reference electrode. And the reference electrode, remember, in this case is a silver chloride reference electrode is the most common. However, if you take a pH electrode, you're gonna see, the silver, reference electrode as well as the indicator electrode. And the indicator electrode, you can see, is just a glass membrane, and inside the glass membrane, it has a capillary, and you feel it, with a known concentration, of HCl. Typically, I think it's 1 molar concentration, that you feel in. And so that's what a pH electrode, really is. And the glass membrane, like I've said, is selective largely to hydronium ion, and that creates, what you call a charge barrier or a charge separation, giving you a voltage, that you record. So I think most of us know glass, is made of what you call siloxane polymer, an inorganic siloxane, crystal, which looks like this. And like I said, it's fairly selective, to hydronium ion, although it also interferes, with sodium ions at the same time. But remember, it's very important when you're using a pH electrode, for it to be hydrated. So often you have to keep the pH, inside a solution, for it to actually work well, so that you can have the membrane hydrated, with water. Because of course you are relying on the hydronium ion migrating inside the crystal. And the only way for them to migrate, the hydronium ions, is if they are carried, by the water as a solvent. So pH electrode always has to be completely hydrated, for it to work well. And as shown in this figure here, you've got the hydronium ions, being captured, by the glass, because of this electrostatic interaction in the siloxane crystal, and you get what you refer to as a charge barrier, that is gives you a signal not a capacitance, sorry, but a voltage in this case. Again, as you've seen, with all potentiometric sensors, they are based on the Nast equation, so the E of the cell is equals to these constants. And again, the constants, like I've said before, they are related to the electrophoretic mobilities of the ions in solution as they get captured, by the glass and so on. And of course, it's proportional, to the hydronium ion, which is what you're looking for. And the 59.16, before I've already said that, it's a constant. So when you're using a pH electrode, like any other instrumentation out there, and of course we've done this a lot in this course, you must calibrate it, because a pH electrode is just giving you a voltage. That voltage means nothing, unless you get the relationship between the signal and the concentration, which is what you're looking for. Of course, the concentration in this case, is a hydronium ion. And so you always, of course, have to do your calibration, and the calibration has to be linear, such that the voltage is linearly proportional to the concentration of the hydronium ion. Ideally, in pH electrode, and almost in all cases, you have to choose, two buffers, to calibrate your pH electrode, and whatever pH you are interested in, should be sandwiched between the two pH buffers that you use to calibrate the sensor. So the rule of thumb is you cannot take a pH sensor and just simply use it. You always have to calibrate it, with two standard buffers. Now, those of us who have, and all of us have used a pH electrode, we know that the data in terms of, the pH readings, tend to be fairly erratic. And the reason it's erratic, is because of a combination of different types of errors, that are especially prevalent, when you're using a pH electrode. And there are many of them, but I'm just going to mention a couple of them. Temperature is a big deal. Remember, potentiometry is an equilibrium type of technique. You're waiting, for the hydronium ions to equilibrate, in the glass membrane. And because it's ions mobilizing or moving from solution to the glass membrane, they tend to be affected, by the temperature. When the temperatures are higher, the equilibrium time is less. And so temperature is one thing, that affects, the pH, and always you need to make sure that the temperature is thermostated. So hopefully you're doing things at a constant temperature, which is never easy. Of course, in a real life experiment, the temperature is always fluctuating, which affects the equilibrium time, and of course affects, the voltages that you are reading. Now, one other error that I've already talked about is a junction potential. Junction potential, an error that results, from the use of the salt bridge. And like I said before, is because of different mobilities, of the electrolytes, inside, the salt bridge, giving you this junction voltage or junction potential. So it's always an error, and I already described before how you can attempt to minimize it. Another very common error, is the sodium error and the acid error. Now, remember, if you're trying to analyze a very acidic solution, you wouldn't be able to get the voltage being linearly proportional, to the pH. And this is because you tend to saturate the glass membrane. So at very, very low pH, meaning very high concentration of the hydronium ion, you tend to saturate, the glass membrane, and as such, the response is not linear. On the other hand, in that you're dealing with very high pH, often in very high pH, you also have a high concentration, of the sodium ions. And we've already said sodium ions tend to interfere, in the detection of hydronium ions with a pH sensor. And so in the very high pH regions also, you tend to have a big error because of the sodium. So it's what is called the sodium error. So take note of that. The dynamic range, therefore, of the pH electrode is not very wide because of the sodium error and because of the acid error. One other problem, with the pH electrode is the equilibration time. So remember, you always have to wait, for equilibration time to happen because potentiometry is an equilibrium technique. And so you have to make sure the equilibration time is always constant, otherwise you get a bit of variation. And lastly, the cleaning, of the pH electrode. pH electrode, tends to be poisoned or contaminated because the moment you've got, the surface, the glass membrane being contaminated, with other type of stuff, then it affects, the migration of the hydronium ions, to the glass membrane. So you often have to clean your pH electrode, so that it's responsive and it's not poisoned. So the next type of ion selective electrode other than the glass membrane is what you refer to as crystalline membranes, and sometimes they call these the solid state electrodes. And maybe a very common example is what you call the fluoride ion selective electrode. So solid state electrodes are based on the use of a solid crystal, or what you call, polycrystallites or even monocrystallites. And the way they work is the following, especially say, for the fluoride ion selective electrode. So you take lanthanum fluoride, which is, a monocrystal. And typically what you would do is you would dope it, with another crystal, like the europium fluoride. And so you would dope lanthanum fluoride, with the europium fluoride. And when you do that, because the valences of europium and lanthanum, are different. So this one is lanthanum 3+, this one is europium 2+. So because of that combination of the two crystals, you create a cavity, in that doped crystal. And the cavity has the size, of the fluoride ion, in the crystal. And so you have cavities inside that monocrystals, that doped crystals, and that cavity is selective, to the fluoride. So the moment you have that crystal here and it's doped, it would selectively capture the fluoride and it's going to occupy, those devoids or those cavities inside the crystal. And the rest, is exactly the same. You have the reference electrode, the silver chloride, and then this one is your indicator electrode, which is responsive, to your fluoride. Okay. And again, as before, the Nast equation is the basis, for crystalline membrane ion selective electrodes as well. All right, so as you can see in this calibration here, the voltage that you get because of the capture of that fluoride inside those cavities would be proportional, to the concentration, of the fluoride. But remember, you've got only so many cavities. So in very high concentration, you tend to saturate the cavities and the relationship ceases, to be linear and so on. And so the dynamic ranges equally would be fairly limited because of that. So, well, this type of crystal, the fluoride, ion selective electrode is very, very selective to fluoride. Remember, like any other ISCs, they tend to interfere often with OH, hydroxide ions. So hydroxide ions are almost the same size as the fluoride, and so, they tend, to occupy these cavities as well. And so you've got a problem with the selectivity coefficient of fluoride and hydroxide, which tends to interfere. For example, you've got a problem like this, and I've shown you this before, that is a Nast equation. and this would be the activity of fluoride, for example. But we've already said, this is the selectivity coefficient, and this is, the concentration, of the hydroxide or the interfering species, okay? Which in this case, it will be hydroxide because, like I said, the fluoride crystals, tend to be, to interfere, with the hydroxide as well. So you may have a problem like this. You've got a fluoride ion selective electrode. It has a selectivity coefficient of 0.1 relative to the hydroxide. And so the question is, what will be the change in electrode potential be when you have this concentration but at two different pH? All right. So you just use the Nast equation. At pH 5.5, the voltage that you read from your fluoride ion selective electrode is going to be that, because the concentration is that, right, of fluoride, plus, K is the selectivity coefficient. And then this one is a concentration of the interfering species, which is the hydroxide in this case. And I hope all of us know this, that you're trying to get the POH, right? Because from the pH, which is equals to 14, minus, the pH. And that's how I'm getting this. And so at pH 10.5, on the other hand, the fluoride is the same, but the hydroxide concentration is different, the POH, because you've got, 14, minus 10.5, right? And that's what I have right there. And so you can see just by sheer change of pH, you get very different readings, because of that interference, from the hydroxide. So this one is very important then to know why you really need to have the pH of the solution constant in this case. So anytime you're using an ion selective electrode like fluoride, often you would use a buffer so that you don't have changes in pH, because as you can see, changes in pH causes problems in terms of change in voltages or readings in general. So there are many other types of crystalline membranes, other than the fluoride that we've talked about. But all of them, as you can see, they are based on the membrane material. You can see it's a crystal, all right? So for example, in chloride, ion selective electrode, the crystal, would be silver chloride, that is doped with something else. If it's bromide, you can see the membrane material would be made from a crystal or a salt made of silver bromide, and so on. You can see you can make lots of different types of ion selective electrodes by choosing the right type of salt that would be selective to the ion of interest. So the other type of ion selective electrode is what you refer to as ion exchange resin membrane. All right. And this one is very, very common, particularly when you're trying to analyze possibly things like anionic or cationic even analytes. Okay. And so this one is based on a hydrophobic membrane that is impregnated with what you refer to as an ionophore. And an ionophore, is a synthetic, often a synthetic material or chemical that has got a cavity, and that cavity is selective to the analyte of interest. So in most cases, you would see an ionophore is often a material that has got a cavity, and the cavity size is equal to the size of the analyte, that you're trying to analyze. So in general, as I said, the ion exchange membrane, typically you've got a plastic, and inside that plastic, you impregnate it, with a molecule. And a molecule can be puckered, it can be puckered, meaning it has a hole, and the hole is selective, to the analyte of interest. Now, one big disadvantage of ion exchange resin membranes is that sometimes they've got fairly low survival time depending on the type of ionophore that has been impregnated. I'm going to give you an example. When you're trying to make an ion selective electrode for potassium, for example, often the ionophore that you use is what you call the valinomycin, which is an antibiotic actually. So you take an antibiotic, valinomycin, and then you impregnate it or you mix it, inside a plastic. And this valinomycin is very selective, to potassium ions. It's not how you make an ion exchange membrane. But I would say that this one is probably the most versatile, of ion selective electrodes. You can make almost anything, just by taking different types of polymers, and then you choose the right type of ionophore using lots of different chemistries out there, that I don't have a lot of time to talk about here, like molecular imprinting. You can choose or synthesize different types of, well, sometimes they call them calixarenes. And these are molecules, that have got a hole in between, that you can use to capture the analyte of interest. So there are many types. You can even make a calcium ion exchange resin, based on using a molecule that looks like this. And then you've got a plastic and a solvent, that can dissolve plastic. And this ionophore is part of that plastic. And you can see you make that membrane that way. And the rest is the same, silver chloride reference electrode. And the other half cell, would be this, which is a calcium calcium ion selective electrode, I would say half cell. And you can see in that case, then you've already made a sensor just by changing the membrane here. So you can see how versatile it is. You just need to change the membrane and you have a different type of sensor. Now, other examples, maybe just to give you examples here, I've already said calcium, you can use this type of ionophore. Potassium, you can use valinomycin, which is an antibiotic, as an ionophore, and so on. And there are many in the literature as well that you can check. But maybe just to explain a little bit, about, say, valinomycin, which is a classical example. See, these are compounds, that have got a hole in between. Sometimes they call them Packard. Sometimes they call them Packard molecules, meaning they've got a hole. And this hole, the size of this hole can fit a very particular ion, like, potassium in this case. And that way you've already made a membrane, that is selective, to potassium. And there are many other types of Packard molecules, like I already talked about, calixarenes, which are completely synthetic. You can also make things like cyclodextrins. You can make many different, you can even do molecular imprinted polymers, which I do a lot in our lab here, and so on, to make different types of Packard molecules. Lastly, the other type of ion selective electrode category or membrane is what you refer to as compound or enzyme-based ion selective electrodes. And again, these ones are very versatile. You can almost make anything, using these types of ion selective electrodes. But the way they work is, for, say, the compound electrode, is where you use a very common type of electrode, such as a pH sensor. Okay? A pH sensor that is glass, and we know that it is responsive to hydronium ion. And all I need to do is I can have another membrane here that only allows certain types of molecules in. For example, I can make a CO2 ion selective membrane using a pH electrode, where, in this case, I've got, say, water, inside this membrane, and then I've got a membrane that only allows carbon dioxide, to seep through. And as this carbon dioxide seeps through into this layer of water, the water reacts with carbon dioxide to make carbonic acid. and carbonic acid changes the pH, of that water, and then you can actually analyze the pH. So in essence, you've seen it's a compound electrode in the sense you've just taken a pH electrode, and then you've added another layer, of a carbon dioxide selective membrane, and that way you have made a carbon dioxide sensor. And so you can use this kind of platform really to analyze any acid gases out there, even say hydrogen sulfide, even say nitrogen dioxide. You can use this kind of platform to make all those different types of sensors. Okay. Now, another way that you can make other different types of sensors is where this membrane is immobilized, with an enzyme. Okay. Remember, enzymes are very, very specific, to the analyte of interest. And that way you can actually make biosensors that way if the membrane is impregnated with an enzyme. Maybe I give you an example. If you take glucose, okay, and then you impregnate the membrane, with an enzyme called glucose oxidase, the product, that often you get is what you call glucuronic acid. And so it's an acid. And so this acid, again, can change the pH of the solution of the water inside. And that way, now you've got a glucose sensor. There are many, many variations, of these type of platforms to analyze many different types of compounds just by choosing the right type of enzyme. You can even make cholesterol biosensor in the same way. You take cholesterol and then you take, an enzyme that is selective to cholesterol, such as cholesterol oxidase, and the product that you get typically is hydrogen peroxide. pH electrodes sometimes are responsive to hydrogen peroxide and so forth. So take note of that. The fourth type of ion selective electrode, they call it compound or enzyme-based ion selective electrode, which, as I've said, the basis of it is just adding another membrane, impregnating it with an enzyme or making it selective to carbon dioxide, and taking a very simple pH electrode and using that, as method of detection. So, well, I have said ion selective electrodes, are selective, meaning is only selective to one analyte. Like I've said, sometimes matrices also can be a problem. Okay, they're not completely selective. And for that reason, the best method of calibrating ion selective electrode is those method that deals with matrices. And I hope you guys already know these by now, that the best calibration method when you have matrix problem is standardization calibration. So if at all I'm trying to analyze, say, glucose or whatever, or urea in blood or in urine and so on, and I'm trying to use an ion selective electrode, the best method, to do the calibration is a standardization, where I take the sample, maybe the urine, I analyze it, and then I spike it, with increasing concentrations, of, say, urea, if that's what I'm trying to analyze, and then I can make my calibration. Very similar to what you guys did with the AAS lab. You can see you create a calibration, a standardization calibration. And remember, the way you determine the unknown is by getting y equals to 0. And so the intercept is minus b over m. And in this case, I plotted volume in the x-axis. So I would multiply this by the concentration of the standard that I spiked, that I increasingly spiked, divided by the volume, of the unknown that I used. Volume of unknown. Okay? And I hope that's clear. And like any potentiometric type of work or device. Factors that affect sensitivity, slope. Remember, slope refers to sensitivity. Things like concentration, temperature affects the sensitivity. Things like stirring, of course, affects the sensitivity. Things like the number of charged ions, very important. Ionic strength affects sensitivity, and so on. The electrode surface, if it's not clean, it's gonna affect sensitivity, and so on. So quick summary, of ion selective electrodes, they respond linearly, generally to the logarithm of analyte activity. So in most cases, you're measuring the activity, okay? I must say the following. In general, the limits of detection can be a problem. They are not very, very low. The dynamic range, which I hope you guys remember what it is, which is the limit of linearity divided by the limit of quantification. That is the range, at which the calibration is linear. In general, they don't have very good dynamic range. All right. Other disadvantages, they tend to they tend to have very poor precision. The precision is not very good, for ion selective electrodes and so on. That's why when you take a pH electrode, it tends to be fairly unstable and fairly noisy, and so on. And also they tend to be easily poisoned as well. Now, advantages, like I've said, they can be very, very small. So you can do in situ detection. So you can actually analyze things in living tissue. They are very, very cost effective. They are very versatile. You can almost make anything you can think of, just because you just need to play with the chemistry to make the membrane selective to whatever you're analyzing. Now, this is very important because you do not destroy the sample. That's a very important advantage, that you're not losing the sample, you're not consuming the sample anytime you're using ion selective electrodes. So they tend to be very good in that sense. Also, they tend to be less affected, by matrices, compared to the other techniques and so forth. So think of other advantages as well that you can add, to this list. Now, I would like us to remember that all the projects that we are working on for the term papers, I would like to add them here later on when you guys give me the posters, by December the 4th, because all of them are going to help us, see the very wide scope of the applications of electrochemical sensors. So I'm going to add sort of whatever you guys generate as your posters. I'm going to post it for all the students to see, so that we can see the very wide scope, of electrochemical sensors, when you're doing for applications, be it in clinical diagnostic, food, and the environment, and so on. So again, I'm gonna post the posters that you give me for every student, to see what each one of us has been doing. And so that's all that I'm gonna say really, about potentiometry. It's a very wide topic, or electrochemical sensors in general. But I hope, from what I have summarized, you've gotten bits and pieces of the scope and the bird's eye view of the application of this important technique, especially in our day for wearable devices.